Okay. How's it going?
Good.
Good? Excellent. So I posted homework 1 as promised on the D2L site. So have you all seen that? And already finished it, right? It's due next Wednesday. It shouldn't, I don't think it will take very long. Let me pull it up just so we can talk about it briefly. Let's see here. It's bigger. You guys see this? Is that okay? Yes? Okay, so first one, as mentioned in class, you have to prove that this is an integral motion with Keplerian dynamics, right? You've all done that before, probably at some point, right? So shouldn't be too bad. All right, the second one, today we'll briefly start talking about this, but this is some more calculus practice for you. And it's not useless, calculus practice, because you'll need these equations that you're driving here and later homeworks and so forth. So basically, in a moment, we'll talk about perturbations from non-point mass gravity fields, so J2 and J3, from this potential, so you can derive the accelerations from this potential. Then we need the partials of those accelerations, right? So when we start actually building filters and talking about filtering next week, we're going to need partials, right? So take the partials of those same accelerations, and I ask you to take the partials with respect to the spacecraft state in the ECI frame, and we're just going to assume that the Earth is spinning about the constant z-axis, okay? So we'll talk about frames a little bit today and everything, but right, we're just using the simple concept of the ECEF frame, Earth-centered, Earth-fixed, centered at the same, center of the Earth, same as the ECI frame. So they're centered at the same point. ECEF spins around a fixed axis with respect to ECI, okay? So we don't have to do any complicated polar motion. So you need the partials in the ECI frame, though, because that's where we're going to typically be fitting our orbits, right? We're going to fit the ECI state of our spacecraft when we do OD, okay? So do that, and also take the partials with respect to the gravity coefficients mu, J2, J3, okay? Questions? Hopefully not? Okay. Similarly, we're going to derive the partials of the solar radiation pressure acceleration. That's in the slides today. Again, with respect to the spacecraft state and CR, which you'll see in the equation if you don't recognize that. And then same thing with third body acceleration from the sun. So assuming our spacecraft's in an orbit about the Earth, right? The state is the spacecraft state with respect to the Earth. In the ECI frame, there's a third body acceleration caused by the sun. We need the partials of that. Okay? Does that make sense to everybody? Hopefully for those of you who might not be 100% clear when we talk about things today, hopefully it'll clarify things. And if not, obviously ask questions. Okay. All right. Then and then the third problem, here you're going to start doing a little numerical testing. So basically, I give you some orbit elements for an orbit. You're going to simulate this orbit using just mu and J2. So it's pretty simple dynamics, right? Not Keplerian, but pretty close, right? Just integrate this system for 24 hours. This is your reference trajectory, okay? And then we're going to look at the dynamics around that reference trajectory. By the way, it is my email, and I don't know how to turn it off. So sorry. That's my next challenge. Okay, so we're going to look at the dynamics around this reference trajectory, right? And one of the ways we do that is with the state transition matrix, right? Does this ring a bell for everybody? I don't have a slide about the state transition matrix today, but I can make one up if we need to, okay? So I need to know if this is unfamiliar territory for anybody. When I say state transition matrix, everybody's like, oh yeah, I know, right? Okay. So remind me to talk about it or ask me a question specifically to remind me, okay? So the state transition matrix then we can use so we're going to start basically a neighboring trajectory, right, with the state deviation vector of 1 kilometer and 10 meters per second off. And this is in, I didn't say this should be in your ECI frame. Okay. Side note, I'm terrible at writing homeworks. So people are always like, wait, did you mean this or this? And usually I don't care, because I just want you to think about it and work on it, right? But you know, if you have questions on things like that, like this I should have said in the ECI. Okay. So if you have questions or things like that, please point them out, because I always forget things. Okay? All right. So we have this neighboring trajectory. So you start with the orbit defined by these orbit elements, and then you add a little perturbation, right? And then you simulate that orbit, and you see kind of how it moves relative to your reference trajectory. Okay? And so there's 2 ways to do that, right? You can integrate the 2 different orbits and see how they move differently, right? Or you can integrate the reference trajectory, create the STM, and use the STM to propagate the state deviation vector over time. Okay? So I want you to do both of those ways and compare how they work. Okay? Does that make sense to everybody? Generally? No? Yes? No? Okay. So I'll leave it at that for now, and we can, if you have questions later. Obviously, there's only 1 class between now and when it's due, right? So if you, I would assume you're going to look at it fairly soon, and then either email or preferably post questions on the discussion board, and then you know, we'll get everything cleared out, or ask them today. Okay? Yes? You guys are all still asleep. I guess I have to ask more questions. All right, so, yes?
Do you want paperless submissions? Just PDFs over?
Yeah, just put them up on the, submit them through D2L. So just PDFify, or, you know, for some of these where you're deriving the partials, if you prefer to do them by hand, I'm fine with you scanning them and uploading that. Obviously, it has to be legible. But, okay? All right, so what are we going to talk about next? So the first thing I want to talk about then is the partials, right? So when I'm talking about partials, we have a system, right? Equations of motion for our orbit, which can generally just be described as x dot equals f of x, right? So x here, typically for us, this is our state vector. And that's typically r and v. Okay? Position, velocity, and for example, if we're doing Keplerian motion, right, x dot is r dot v dot. And so what are the equations of motion that would go over here? So r dot equals v, yep, and v dot equals, for Keplerian motion,
Due to gravity.
yeah, so it's minus mu over r cubed, times r. Okay? All right. So when do we use partials? Like, why do partials even come into our discussion and our language when we're talking about filters or dynamics or anything? Why do we need partials? Yeah.
Is it for linearization?
Yeah. And linearization is basically just a truncated Taylor series, right? So a Taylor series, you take a bunch of partials, right, of increasing orders, right? Linearization is just a first-order Taylor series, right? So let's linearize our dynamics here. So if we, I'm going to skip a step. Hopefully it's okay. So if we get the first order, the linearized dynamics, basically what we get, df dx times delta x, right? Is everybody okay with how I got here? Right? Technically, you have some x dot star and plus x star, right? But I just cross those off, right? So this is the linearized. This is just the linearized dynamics now about some reference trajectory, Okay? So oftentimes you'll see something like this, x equals x star. What does that mean?
You evaluate at the reference.
Right. We evaluate these partials along some reference trajectory, which is given by x star. Okay? So let's break this out a little bit more. Make sure everybody's on the same page here. So we have dr dot with respect to r, right? Dr dot with respect to v, right? So we're just kind of writing in block matrix notation. I'm having trouble speaking this morning, sorry. So we're taking the partial, right, of f of x, which is x dot, right? Partial of f with respect to the state. So with respect to r and then with respect to v, right? So we took the first component here, take the second component down here, v dot with respect to r, v dot with respect to v. Bless you. Okay. So first of all, just as point of notation, these guys, the same thing, right? That's oftentimes called A, right? In linear systems, lots of times you see a linear system is x dot equals ax if there's no external forcing function, right? Okay. Another aside, quickly, is that when you're going through Dr. Bourne's book, he uses for your nonlinear state capital X and for your state deviation small x. Okay. I tend to use x and delta x, right? Like I said, I'll change notation on a daily basis, so this will help keep you on your toes, especially at 8:30 in the morning, right? But that's what's going on. So when you look at that, it'll look a little different, but you have to learn to look past notation, right? Recognize the equations for what they actually are, right? So that's how I justify my laziness, okay? All right, so then what am I missing here? Sorry, Matt, one sec.
Sure.
Let me fill in this last thing. What do we need over here then? Right. So let's break delta x into components so we can write this as delta r, delta v. Right? Okay. Question?
So just a point of clarification, you've got partial f, partial x, and when you wrote it out as a matrix, you've got r dots and v dots. That's because you defined f to be x dot.
That's right.
First place. Okay.
That's right. Yep. So yeah, you could. This is really partial of f with respect to partial of r, right? But it's really f sub 1 or something, right? Because it's just the first half of f. So that's why I use r dot and v dot. Otherwise, I have to make up more notation that doesn't make sense later. Okay? But these are just, this is just another way of saying it's your dynamics, right? You're taking the partials of your dynamics. Okay. So, given that we're looking at the Keplerian problem, right, where the dynamics are here, 3 of these are very easy, right? So what are they? So delta r dot with respect to r. What's that?
0.
Right? Everybody agrees with that? You should shake your heads or I'm just going to keep asking you questions. Like, yes. Okay. All right, so what's delta r dot with respect to v? Where I is an identity matrix, right? And just to be clear here, this is a 3 by 3 identity matrix. Okay? All right? So what is the, which one of these is really easy?
Dot is usually
Delta v dot with respect to what? Respect to r? Equals 0? I don't think so. Right? Here's v dot.
oh, sorry. Vector v.
Yes. That's only an excuse for like the first 2 weeks, okay? All right, so those are all easy, right? So a lot of this simplifies very easily. But of course, the one that doesn't simplify as easily is, let's go down here, delta v dot with respect to r, right? So this is partial with respect to r of this guy, right? Minus mu over r cubed times r. Okay? So, who's awake enough to do this? Nobody? All right, so let's do the easy side first, right? We can use the product rule here, right? So let's take the partial of this one times this one. All right, so what does that equal?
Negative mu over magnitude r cubed.
Is that it? Thank you. Right. Times I. Remember that the partial of a vector with respect to a vector becomes a matrix, right? Increases its size in tensor notation. Right? So that one's easy. Okay, how about the second one? First of all, I think an easier way to write this is, how can we rewrite this? R dot R to the 3 halves. Right? That's what this guy is. Okay? So, and really, since it's on the denominator, it's kind of like R dot R to the minus 3 halves. Right? So I'm going to walk you through this slowly since you're all asleep. Okay? So we need somehow plus mu, sorry, minus, because there's already a minus sign there, minus mu times r, which is this other term, right, and times the partial of r dot r to the minus 3 halves. Right? Okay. I've gone far enough. You guys can do it. We're awake. We're feeling loose. Do we need to do like calisthenics at the beginning of class? What's the partial of this guy? Let's go.
Negative 3 times that quantity to the negative 5 halves times r.
Negative 3, sorry, I'm just catching up to what you said, times that quantity, is that what you mean? To the minus 5 halves times
r.
Yes. And so since the negative cancels with the negative, we're going to get a plus out front. Right? So we get plus 3 mu r transpose r to the 5th. Okay?
And to get that r transpose, you just know it needs to be a 3 by 3, so that's why.
Yeah, basically. Yeah, you can, yes. That's the easiest answer, right, is to just kind of, you know that it has to be a matrix, so you have to check your math, right? So the official way, if, you know, there are different ways to write it, like in tensor notation or something, or index notation, where you can see that it has to be, if you rewrite it in matrix notation, it would be a transpose, right? But, or you can just kind of know what's coming, right? Okay, so you have to take a bunch of partials in the homework, which now I'm very happy I assigned because apparently everyone's too tired to do them. So you need practice. Okay. So also, as a side note, right, we did this all in matrix vector notation, right? You don't technically have to do that, of course, right? You could write everything out in components and do it component by component, okay? This is much more efficient, right? So once you get comfortable with vector notation and actually doing the calculus with vector notation, it's a lot faster. So I recommend getting comfortable with that. But if you're not sure about your answer, like, for example, if you had R, and you didn't see the transpose, you're like, well, it's supposed to be a matrix, and also 2 R's next to each other don't make sense at all. So what do I do? Is it supposed to be a dot or what? Right? You can use the component form to check that. Right? So you could do it. You could break your R into X, Y, and Z. Take the partial with respect to X, then Y, then Z, right, to check how it all works. Okay? Does everybody feel comfortable with this? Okay. Good. You get to practice. All right, so back to the point, I guess, is so why are we linearizing and taking partials and all that?
Want to simplify the math for a computer?
Computers are pretty smart.
Want to use linear algebra to propagate our states forward. So we should have a linear A matrix.
Okay. I'm not sure wanting to use linear algebra is necessarily the right statement, right?
How we do all of our filtering. It's built on linear operators.
Yes. That's, I think, what you're getting at, right? So our Kalman filter, right? Kalman filter assumes linear dynamics, right? This, right? These dynamics, are they linear? No, not at all, right? So immediately, if we want to apply a Kalman filter, we need the linearized dynamics, okay? And so we're going to need these partials so we can write this A matrix so we can do the linearized dynamics, right? So just because I'm thinking about it as a quick aside then, phi, so this is your STM, right? This is going to be like your 1-minute refresher on STMs. And if this isn't enough, then look in Dr. Bourne's book. Okay, I don't know the page off the top of my head, but there's like a multiple-page section where he derives all the properties of STMs. Okay, I think in chapter 2, I'm not positive. Okay, so what's the STM? How do we define that in terms of partials? Anybody?
So, isn't it the partial of your state by the original state? Like dx by dx naught?
Yep. It's just to be clear here, to match the other side. All right. This is all the STM is. Okay? So it's the partial of some value of the state at some time t with respect to the partial of the state at some other time t naught. Normally going forward in time, but STMs can work both ways with linear systems. Okay? So, again, typically we have to, not typically, but if it's actually a nonlinear system, you have to evaluate this along a reference trajectory. Okay? So this is, if it's a linear system, you can just evaluate it, right? It just falls right out. Okay? So, how do we, well, first of all, what can we use that for then? What's the STM used for? This is what you're going to use it for in your homework.
Taking an initial state and propagating it through some reference.
That's right. So, whoops. So, dx at time t equals phi times tx at time 0. Okay? So, if you plug back in the partial, you would see basically that kind of the dx's at time 0 cancel out and you get the state at some future time. Okay? This is what you're going to do in your homework, right? I'm giving you this dx naught. I'm telling you find the state transition matrix and then you can compute the time history of this state deviation vector. Okay? So, next question then is how do we find the time history of the state transition matrix so we can do that? What's the equation that governs the dynamics of the state transition matrix? Phi dot equals what?
Is it just A something?
A something, yep. I'll give you the A.
It's A phi,
Yeah.
and then the initial conditions are just identity.
Okay, and so what do you mean by the initial conditions?
So state transition matrix from T naught to T naught is identity.
T naught equals identity. Right. And of course, if you look back at the definition, that makes perfect sense, right? So if you said T equals T naught, so you have delta X naught equals phi times delta X naught, phi must equal the identity matrix, right? So that's your initial conditions. Your dynamics are this A matrix, which we, for Keplerian motion, we just derived on the previous page, right? This is the partials, df dx, okay? So this is a matrix ODE, which just means it has n by n components instead of n by 1 components, right? And of course, they're coupled. Okay? So, integrate this along your reference trajectory, right? That gives you a time history of phi. Then you can use that to give you the time history of the state deviation around the reference trajectory at any time. Okay? So, once we get phi, and you have your state deviation vector, say in the homework, right? It's some specific vector, and you can figure out what the time history of that is. What if I want to look at a different initial delta X naught? Do I have to get a new phi?
No.
Why?
Because the deviation doesn't affect your A matrix, which is what is propagating phi forward.
Right. So your A matrix and your phi along the way through this equation, but your A matrix is evaluated around the reference trajectory, right? It's not, it has nothing to do with the deviation. It's evaluated at the reference trajectory, okay? So you have some X naught, right, goes off into space. There's X at some later time t, right? You would define phi along the way such that for any delta X naught, you get a delta X t, right? That's, of course, using phi with this TF or whatever, but you could do it anywhere along the way, right? And you could do it for any delta X. And, of course, delta X is a 6-dimensional space, not a 2-dimensional, right? Okay. Is everybody with me? Marginally? Right. You've seen all this. Everybody has seen this stuff before, right? This is starting to ring bells. You've seen it all in either 5044 or 5070, whichever one you took, right? And possibly in many other classes, right? Anyone who took linear controls has seen this to death, right? Right? Okay.
I think linearization was, what, 1 lecture in 5044?
Yes.
Lectures.
I wouldn't say that we're experts in it.
Oh, you will be.
But right now, I can tell you, we're not.
Okay. So that's okay. We can practice more. All right. So the first homework will be useful then, I think, right? And we'll talk more about, so in 5044, you mostly talked about linear systems where this is valid for a linear system, right? All this talk about state transition matrix and phi and, you know, state deviations. State deviation in a linear system is just your state. Okay? So phi works for any linear system, right? And this is a kind of a fundamental part of the time update component of a Kalman filter, right? So everybody's seen plenty of that, right? Everybody has programmed Kalman filters for linear systems, right? Okay? So I know you've all done this before. Okay, you just have to refresh your memory. So here the difference is, instead of A just being the dynamics, we have to get A by linearizing the nonlinear dynamics. Okay, so it's kind of one extra step, but then the idea of the state transition matrix is identical. Okay?
So how does this fit? So in a linear system, you'd see something like x dot equals ax.
Mm-hmm.
So I feel like this must collapse into that. And if you do the right thing, and I'm not seeing what I need to do to collapse this into a...
Okay. So your full nonlinear dynamics are x dot equals f of x in this course, always, right? We don't deal with linear dynamics. Okay? We're doing orbits now. All right? So the linearized version is now delta x equals a, or delta x dot equals a delta x. Okay? But again, it's basically the same thing, right? This is basically x dot equals ax, right? And so that governs the motion near the reference trajectory. Your full dynamics are still actually given by this, right? So when we have the linearized dynamics for delta x, coming back over here, so what are we saying? So this full reference trajectory, whichever line that was, whatever, right, this is governed by x dot equals f of x. Okay? Right? So those are nonlinear dynamics. That does not equal ax. Okay? Now we're trying to say that we can propagate the state deviation vector, which is some state nearby to the full nonlinear state, using phi, right? And we did this by linearizing these dynamics, right? So if we write out the kind of the approximation here, what we have is that x dot star equals f of x star plus this a delta x. Sorry, we should have the, oh no, my beautiful drawing. That doesn't match anymore. It doesn't, okay. Right, sorry, x dot star plus delta x dot. Okay, this is a star, not a dot. Don't worry about that. X star. Okay, right? So this is how we've approximated this. Is this side exactly equal to f of x? Right. So it's, we should have plus higher order terms here, right? We just knock those out. So we're approximating the dynamics of some state near the reference trajectory by the actual nonlinear dynamics along the reference trajectory plus these linearized dynamics. Okay? So f of x star equals x dot star. So those go away, and we have delta x dot equals a delta x. Right?
Okay. Got it. Cool.
Cool? Okay, so one more question then on this. What if I say this is my delta x naught? Can I still use phi?
It's still within a realm of here. It's good linearization.
Right. So there's notionally some region where this approximation is a good approximation to the dynamics, and it will give an accurate prediction of delta x into the future. Okay? If you have too large of a state deviation vector, this will not be a good approximation. And if you applied, so this could be your delta x at t equals from phi, right? But if you actually just took this and applied the nonlinear dynamics, it might go over here. Okay? So at some point, if you get too far away from your reference trajectory, using these dynamics is not a close approximation. You shouldn't have dropped these higher order terms, right? So that's garbage. Okay? So when we're working with state deviation vectors, anytime they start getting large, and this is a totally relative term, large, right? And there's no real way to answer what's too large without just, I don't know, experimenting basically, right? So if delta x gets too large, you can't use phi, okay, along that reference trajectory, okay? And this is basically what I'm having you look at in that homework assignment, right? So you'll integrate the state deviation vector once with phi, you'll do it once with just f of x, you'll see how the two differ. Okay? Does everybody think they're on board to do that, to do the homework? Okay, good. Cool. All right. So let's go back to some slides then. Okay, so let's talk a little bit more about dynamics. So we've looked at the Keplerian dynamics, and basically those come from a potential system, right? Gravity is a potential, right? You take the partial of the potential function, you get the acceleration on the body moving through the potential field. That's what gravity is doing, right? That's all the Keplerian problem is, right? So you can, what's the potential for point mass gravity?
Negative mu over r.
What's the potential, though? What's V?
Yeah, isn't just mu over r?
It's mu over r. It's not
Yeah.
negative.
Okay, I see.
The acceleration then is, sorry. Okay? All right. So this is just kind of an aside, but we'll use this again in a moment, right? So, right, the potential is minus the potential energy, which is mu over r, right? That's what Don just said. You take the partial of the potential, or the partial of the negative potential energy, you get the acceleration. Okay? So this is all pretty trivial for Keplerian dynamics, but in a minute we'll reuse this to understand how satellite moves when there's other non-point mass gravity acting on it, right? Okay, so just to, before we do that, for a second, back up and talk about perturbed motion, right? So all this is, when we say perturbations in astrodynamics, really we're just saying anything that's not the two-body problem. Okay, so normally we're talking about Keplerian dynamics, two-body problem, right? So your acceleration is just this minus mu over r cubed times r. So any other acceleration that's acting on the body you're looking at is a perturbation to the system. Okay? So the term perturbation, though, implies what about A? About this A that I have written here.
Small relative to the first term.
Right. Perturbation implies that it's small relative to your original term. That's not always the case, right? So when a launch vehicle is putting a satellite in orbit and it's firing its engine, is that a perturbation? Depends, right? Everything, the answer is always depends, just guess. Depends, okay, right? For like a typical, you know, Atlas V type launch vehicle, no, right? The thrust produced is much, much greater than gravity. Okay, so you're not really following Keplerian dynamics plus some, you know, tweak to that from this perturbation. You're following these totally different dynamics, right, while your engine's on. If you're a spacecraft with a low thrust system, right, then it's more of a perturbation, right? And the key to why saying a perturbation is small versus not small is that, you know, there's a whole field of mathematics called Perturbation Theory, and that basically is taking a Taylor series expansion, truncating it, usually to first order, like we just did, right? So you linearize the system and see what the effect of this small perturbation is in a linearized sense. Or maybe you would keep the second term, right? But if your perturbation is not a small perturbation, then that doesn't make any sense to do. Okay? So, planetary mass distribution, right? So, of course, we talked about this with Keplerian dynamics. We're assuming point mass gravity, which is equivalent to constant density sphere that we're outside of, right? I mentioned that last time. But that's never true in reality, basically for anything. So we need some way to understand how to determine the gravity and the gravitational acceleration for some body that's not constant density sphere. Okay? And theoretically, or like officially, the way you would do it, right, is you could go and you integrate over the whole body, kind of like pictured here, right? For every little infinitesimal piece of mass in the body, you figure out what gravitational acceleration it exerts on your spacecraft. But that would take forever, right? And you'd have to know the exact mass distribution of the body to figure this out, right? which we typically don't know. So the way we do it, with no derivation whatsoever, okay, please see one of many textbooks, because we don't have time to derive this, right? But what we do is we add an extra potential that comes from the fact that the mass distribution is not, that the body is not a constant density sphere, okay? And the most common way of doing this is using a set of spherical harmonics as shown here, right? So you have the spherical harmonics, which are these J and all the C and S terms, and they get multiplied by these Legendre polynomials, and that gives you basically this U prime term, which is like the extra potential from the fact that the body is not a perfect constant density sphere. Okay? So in kind of some of the terminology here, the L that you see here is called the degree. The M is the order. Okay? What's the relationship between J and the C and S? So first of all, the J terms are called the zonal harmonics, right? And how are they related to the C and S terms? Anybody know?
There's a zero order of this.
Yep. There's C, L, 0. But there's one other trick, of course, because it can't be easy. They're also the negative of the CL0 terms. Okay? So just to make sure we have that down somewhere. So if we have JL equals minus CL0. Okay? So this is just a historical notation. Okay? So when we come back over here and look at this, sometimes you'll see this written, right here we have U prime written with two terms, right? There's the first term, which is just the effect of the zonal harmonics. And then there's the second term, which is all the tesseraal and sectoral harmonics, okay, which is these other terms, right? So really you can collapse all these. You'll see that the second term here for for M starts at 1, right? You can rewrite this, say, in this second summation inside here. Sorry, I keep pointing at that and forget you can't see it. You could start this at M equals 0 and use the J's become C's, right? And you just wipe this term out, okay? So it just gets incorporated here. The math ends up being all the same, okay? Because the minus sign is already right here, right? The difference, okay? So you can just block that out, change this M to 0, and away you go. Okay? Question?
How does it wrap up C and S, since those two are out of phase with longitude?
Say that again?
It seems like C and S are basically out of phase as you go around in longitude. How does the J term wrap up the S?
So S,
Does not have
L,
zero.
comma 0, right? S, L, 0 is always equals 0. Okay, so, and that comes out of here because if M equals 0, here, what's the sign of 0? 0, always, right? So this means nothing, right, at the 0th order. Okay? Don, you had a question?
Yeah, I was just wondering, is there a reason why in the U prime it's mu star instead of just mu?
No, that's just wherever I pulled this from.
Okay.
It's mu star equals mu. It's the same. Okay. Yeah, it should be the same as this one. Okay. So I think the reason people usually write it, or not usually, usually I think you'll see it as the double summation in most textbooks without this first term. Sometimes people like to do this because for planets, for lots of planets like Earth, the zonal harmonics are most important. So if you just wanted to do the J terms, this is a nice way to just see how all the zonal harmonics show up and you could get rid of this guy, right? So it just kind of makes it come out. But ultimately, this double summation is what's actually defining the potential, okay? So the other terms in here, So this potential is defined in the spherical coordinates locked to the body. Okay? So r is the radius, of course. Then phi, which you see inside the Legendre polynomials, right? Phi is your latitude, right? And then lambda is your longitude. Okay? Right? So that's evaluated in the body fixed frame. Okay? So if you have a body like Earth that's spinning, you have to get your coordinates in the body fixed frame to figure out what the potential is. Okay? So you can't just use your ECI coordinates to figure out an ECI latitude and longitude, because that doesn't make sense, right? Because the gravity field turns, gravity potential turns with the body that's creating it, right? It's the mass distribution that's creating it. Okay? Right? So for Earth, basically, right, it's just kind of a slightly flattened sphere, right? So we have a J2, that's the main component, because that basically represents this oblateness. It's pretty spherical in mass distribution, right? So C22 and S22 are what end up defining kind of, if this was looking down from the North Pole and it was shaped like an ellipsoid, you would have a non-zero C22 and S22. Okay. When we look down from the North Pole, though, it still looks pretty much like a sphere. Okay, our geopotential. So that means C22 and S22 are pretty close to zero. They're not zero for the Earth, of course, but they're not nearly as large as J2. Right, so there's much more of a polar flattening than kind of a equatorial flattening. Okay. J3, then, you can look all this stuff up, on Wikipedia or something if you're interested in what all these spherical harmonic functions kind of look like. So J3 kind of makes a pear shape to the geopotential, right? So it makes it, depending on the sign, it makes it either smaller or larger at the north or south pole, kind of like is drawn here, right? Okay, so this is not the, well, with J2 it is kind of the shape of the Earth, right? The Earth is physically kind of flattened, right? But for the rest of the components, it's not actually representing the shape of the Earth, right? It's the shape of what? Yeah, like the geopotential, right, of the gravity field. Okay, so the Earth does not look like a pear, but the mass distribution is not uniform such that the potential has this pear-ish component.
But even then, that's just a description of the perturbations at that order.
That's right.
Looked at the kind of qualitatively, you would still say it just looks like an oblate sphere.
Physically, the Earth looks like an oblate
Well,
sphere.
even the geopotential field, the potential field looks like a sphere.
Yeah, for Earth, it's hugely. I mean, look at the difference here, right? So J2 is 3 orders of magnitude larger than J3, for example, right? So it's hugely dominated by J2, by the second order gravity field. Okay, so this is when you cut off your U prime at a particular degree, you're truncating your accuracy of the gravity field, right? Depending on the accuracy of the orbit, propagation that you need or care about, that might be okay or might not, right? And when I say accuracy, that means, obviously physical accuracy of propagation, but also that's tied to time, right? So a small error in your dynamics, if you're going to propagate for a lot longer, you need your dynamics to be much more accurate. And if you're only going to propagate for, a few hours, your dynamic model can be less accurate. Okay, so that goes in with the accuracy. Okay, other questions on this? We can't get too deep into this right now because we don't have time. Right? So for the homework, I ask you to look at J2 and J3, right? So you only need to look at this top guy, right? You can just throw that guy away, okay? So that's all you have to worry about for the sake of the homework, okay?
R is
same as mu, yeah. Yep. Okay. right? So those are the values. You can also find the values like in Bourne's book or lots of different places. Okay, so our orbit energy has changed, right? Because if compared to a Keplerian system, right, we've plunged our spacecraft now into a different potential field, right? So if it's a different potential field, it has a different potential energy associated with it. So you have a different orbit energy, right? The orbit energy, this specific orbit energy is just kinetic plus potential energy, right? It's nothing secret or magical. Okay, now we have a different potential energy, so we need to represent that. Okay, and that's where that U prime from the 2 slides ago comes in. So now the question is this constant? Anna's shaking his head. No? Louis? No? Depends. Awesome. Excellent answer. Okay, what does it depend on? Jorge?
On what you define your system to be.
Okay, be more specific.
So if you're looking at the spacecraft, for example, then, or I guess the orbit of the spacecraft, then the energy would be constant because you've got
Perturbations from, if it's orbiting around the Earth, then you've got perturbations from the Sun, the Moon, etc. But if you look at the solar system as the system, then your energy would, if you look at the effects on the spacecraft's orbit as well as the Sun's orbit, the Moon's orbit, all that, it all ties in together, and then at that point energy would be constant.
Right. So I think what you're saying is energy is conserved, right?
Right.
Which it is. Okay? Energy is conserved. Is this expression constant? Tivo?
Prime is derives from a potential or not. Conservative. But
Yeah, okay, so we're going to assume it's this U prime, okay? So is this constant?
General, no. Sitting on the ground here, we're not moving, so we're in the same place in the potential field all the time, so it is for us right here. But for a spacecraft, that U prime varies with latitude and longitude, which are constantly changing for so no, potential energy won't be conserved, but changes to the spacecraft will. The energy is kept in the system because the spacecraft changes velocity.
Right, so the total energy is conserved, right? But this particular expression is not conserved, right? You nailed it, right? We're moving through, and U prime is not constant if you're moving, okay? So if you're standing still, right, it's this very special case where, yeah, this would be conserved, you know, but we're not really in an orbit, right? We have normal forces keeping us up, right? If you're a spacecraft in an orbit and you look at this function, it won't be constant, basically, right? Of course, it depends on what all the coefficients are inside U prime, okay, in the specific orbit. Like you could find a specific orbit that has a constant U prime with specific coefficients, right? There do exist those solutions, but that's not the normal solution.
Maybe I'm misunderstanding, but are you saying that then that's the potential energy only and not the kinetic energy?
So this is your kinetic energy, right? V squared over 2, your specific
Right.
kinetic energy.
Yeah.
This is your potential energy from the geopotential, right? But what's happening with the geopotential?
You're moving through it, so it's changing.
Yeah, right? You're not staying in the same place, okay? And typically, especially with the Earth, what's happening with the geopotential? Not you, what's happening with the geopotential?
It's changing all the time.
It's moving too, right? The Earth is rotating, right? Okay?
Now I'm confused, and I feel like my answer is wrong based on what Jorge just said. Because any change to that potential energy is going to move into kinetic energy. There's a kinetic energy term in epsilon.
Mm-hmm.
So why is epsilon not conserved then?
So your specific orbit energy is not conserved, right?
Everything, potential, all the energy should still be transferring between potential and
right?
they're both in specific energy.
Right.
Why not?
So your specific, sorry, I think I'm the source of the problem, right? What's your specific orbit energy? Right?
Body's energy divided by mass.
It's just those two, right? That's your specific orbit energy, right? And then we have this perturbation term, right? What did we look at last time? We did E dot, which equals this, under Keplerian dynamics equals 0, right? So what is E dot if you don't have Keplerian dynamics?
Well, your velocity's changed as well, right? Because it's affected by the perturbations.
Well, your dynamics are different, right?
So why doesn't the new velocity derivative, when you go to take that derivative, cancel out the perturbation?
Right. So this is why I think I was the source. I was asking this in a confusing way. I'm sorry. So if E equals your normal specific energy, right, like we normally think of, V squared over 2 minus mu over R, if you put yourself in a potential field, you know, with J2 and J3 or whatever, that's not conserved anymore, right? So your original specific energy is not conserved. If you add this back in, is it conserved? Right? Because the energy is conserved, right? Sorry.
So in this case, if you get rid of the perturbations and your system is the spacecraft's orbit, then that's like your energy is conserved. But when you're adding perturbations, it's like it's an external energy source, I guess, and so your system's receiving that's why it's not conserved anymore, because that U is coming from external to the orbit. It's not two-body anymore.
Yeah.
Right?
So if you think about it in a two-body sense, right, you think about your specific orbit energy, which we relate to, right, this guy without the mu prime equals minus mu over 2a, which is how we get semi-major axis typically, right, which is how we think about orbit energy typically. Okay? That's not conserved as soon as you have any of these other gravity coefficients acting, right? If you write this, it is conserved, but that's not equal to minus mu over 2a, right? So there's a disconnect in there somewhere, I guess, is what I'm pointing out. So
It's constant, but it's not minus mu over 2a.
that's right. That's right. So this whole term is constant, but what I would still say that your orbit energy, okay, and this is where it gets confusing, right? Because your orbit energy is typically still defined by this, which is now not conserved. Okay, that's terminology, your orbit energy, right? Your specific orbit energy is still just V squared over 2 minus mu over R. Your total energy of the system is this expression, which is conserved.
So it would almost be easier to think about.
Right. Right. Okay. So now I've confused everybody. We're just going to end class. No. Okay. Seriously, though, are we all on the same page now? Hopefully. If not, ask a question, because I don't want to leave you more confused than I found you. Right? So another way of saying this is your semi-major axis constant?
No, it won't.
No.
No. Right? Okay. So let's do this. All right, so your normal orbit energy equals V squared over 2 minus mu over R. That equals minus mu over 2a, right? That's your semi-major axis, A. Okay. We know that under Keplerian dynamics, E dot equals 0, which of course you can, so under Keplerian, E dot equals 0, A dot equals 0. Okay? So now, when we don't have Keplerian dynamics, so now we'll just say with J2, E dot does not equal 0. A dot, therefore, does not equal 0. Okay? Chris?
Couldn't we similarly say that the semi-major axis is conserved, but mu is actually not conserved because, in effect, if we have those perturbations, we take into consideration the fact that the gravitational potential is different, and mu represents the gravitational potential of this point mass of the planet. So
no, I wouldn't say that because you're right in that the potential is not. It's a different potential now, right? That's why this is not conserved. Mu, though, has a very specific definition, right? It's G times M. Okay?
Yes.
And no matter how M is distributed, it is whatever the mass of the planet is. Okay? So mu, even for a crazy, shaped asteroid, mu is constant, right? Whatever the mass is, that determines what your mu is. Okay? But then the fact that the mass is spread out in some weird way is what gives rise to all these non-zero, C and S, spherical harmonics coefficients. Okay?
thank you.
If you are in a geosynchronous orbit, even if you apply the J2 term, would that still be true that E dot is different than 0 and your semi-major axis is also different than 0?
So again, there are special solutions, right? So this is way beyond where I wanted to go, but that's fun. That's fine. It's fun. Okay, so if this is the Earth, we're looking down from the North Pole, okay? So the geosynchronous region is some constant semi-major axis out here, which is a perfect circle like I've drawn it. And if you just had J2, right, where would you have a constant potential on this circle? So we're looking down, we're saying this circle is looking at the equatorial plane, okay? So where on this circle is the potential constant if you just have mu and J2?
Everywhere.
Everywhere, right? So if you are perfectly on geosynchronous orbit and the potential is just mu and J2, right, your potential is never changing, right? You've kind of found one of these specific solutions, okay? So the Earth is actually somewhat elongated. I'm always a bad illustrator, drawer, but this is that's my latest excuse, is that that's not stable. Okay, so now it's not actually a sphere when looking from above, it's elongated in some way, right? So depending on how you write the axes of the system, you can write it as there's actually a non-zero J2 and there's a non-zero C22, okay? So now if you have J2 and C22, where is the potential the same? Yeah, it is symmetric. Let's call this direction X, this direction Y, this coordinate system. So
if
how is it symmetric?
J2 and C22 are the same, then a polar orbit might be.
They're not the same. Okay.
So if they're not
the same, they're just non-zero. Okay. We're looking at the equatorial plane here, right? Right. So basically you get, yeah. So this is along the y-axis, this is along the x-axis. Okay, so there are 4 points. The energy is not the same here, or it is the same here and here. It's not the same here and here. Okay, and it turns out that, let's see if I do this right. Yes, these, I believe, are the stable equilibrium points in the system, and these are the unstable ones. Okay, so it actually turns out in the Earth's gravity field there are like 4 equilibrium points like this, which are places where if this is the stable one, if you were in a neighboring orbit, you would stay there, right? And if this is the unstable one, if you were in a neighboring orbit, you would go away. Okay, and this simple model of the dynamics is what dominates operations in the geosynchronous belt. Okay, this is the best place to be in a fuel efficiency sense, right? Because you kind of don't have to station keep, you'll just stay nearby, right? This is a terrible place to be because if you don't station keep, you'll go all the way around, effectively. Okay. Of course, it also matters what's underneath here, right? So I don't remember exactly where these are. Alexa?
Isn't it between the points, you mean?
Yeah. Do you remember
Between the
where
sun?
No, I mean, does anyone know where these are over the Earth, like at what longitude? I think one of them is like over the Pacific Ocean or something.
5 and 1's 170.
Something like, yeah. Well, yeah, we can Google this if we want, right? So, of course, the other thing that dominates geosynchronous belt economics is what you're over, right? So if you're just over the ocean, it's not as valuable. Okay, wow, we are way off track, guys. All right. I'm going to keep going. Nope. We're skipping this. Okay. We're skipping the second question, but this is a new point for you. And that is that, so remember, you can't, your integration constant, if you were going to use your old orbit energy, wouldn't work. This term now, which equals k, is something you could use for an integration constant to check the accuracy of your numerical integration if you wanted. So this omega c is the spin angular velocity vector of the Earth, right? Dotted with the orbit, angular momentum, and then you have this whole potential in here. Okay, so this kind of captures everything. I'm not going to get into that because I'm already way too distracted. Okay, quick note on drag, right? So I think the most important thing to note about drag is when do we have to worry about it?
Leo?
Yeah, so roughly what? You have an altitude?
Hello, sorry.
Yeah, I would say probably 1,000 to be safe. Right, so 1,000-kilometer altitude and below. If you go below 1,000-kilometer altitude at any point in your orbit, you should be worrying about this. Okay. So what's the altitude of most LEO spacecraft, roughly?
400.
Yeah, I would say like 300 would be more typical. A couple hundred. Okay, I think what's the ISS at? It's only at like
400. Kilometers or miles?
Huh?
Kilometers or miles?
Kilometers. 400, right? So, right, in that range, right, you need to worry about it. Now, the other big one so all LEO spacecraft, it has a large effect, right? That's what limits the lifetime. That's, of course, how LEO CubeSats work, right? We just throw them up there and don't care about them because we know they're going to come back into the Earth's orbit, right? Or at least that's the current concept of operations. What about GTO, right? So you use a launch vehicle, you put something, on a GTO trajectory, so a spacecraft's going out to geosynchronous orbit. The launch vehicle stays in this GTO orbit, right? So what happens to it over time?
The periapsis decays.
Right, so your periaps for those guys is typically only like, 100 kilometers or something like that, maybe 200. Okay, so it's really low. Okay, so they end up decaying pretty rapidly, right? Which is, again, the same idea, that those spent upper stages should come back into the Earth's atmosphere, somewhat soon, right? So we don't have to worry about them. Okay? So classically, if you're looking at orbit theory, right, it has two main effects. It removes energy, right, as drag, removes energy, so your A changes. This got kind of messed up because it went to the next line. But dA dt is less than 0, right? So your orbit energy is decreasing, your orbit size is decreasing, and then also dE dt is less than 0, right? Which means what? If you're in a GTO orbit, what's happening? You're circularizing, okay? So if you're in a circular orbit, is dE dt less than 0? It's 0, yeah. Okay, you can't get negative eccentricity. Okay, so once you reach a circular orbit, so this is also, by the way, the concept for aerobraking, right, when we go to Mars or something, right? You go into a highly elliptical orbit and then you just let the atmosphere bring you down and circularize you, okay? So we like it at Mars, we hate it at Earth. Okay, I'm not gonna let you just guess these because I've made you guess enough things today. Here's kind of the laundry list of other forces that we'll typically worry about. Again, whatever perturbation this is, right, depends on your application if you really need to worry about it or not. So, you know, the other day I was talking about relativistic effects, right, like when is that important or not, right? Those are really small, so you have to have really high precision. You have to be worried about really high precision to care about that. Thrusters obviously can be large. Solar radiation pressure is pretty small, but it adds up over time because it's always there, right? So that's usually something you want to worry about. N-body gravitation, so basically third body effects from the sun and moon. When do we need to worry about those?
When you're away from the Earth.
Yeah, I mean, they get stronger as you go away, as you get farther away, right? So you worry about them more as you get further away. You worry about everything if you're trying to do really high precision stuff like, you know, GRACE or ICESat or JSON, something like that, you know, where you're doing really, really, you know, centimeter level OD, right? You need to worry about everything then. Yeah, so we don't need to talk about all these. So then I just have two particular models here because these are the ones that I want you to look at for the homework and that we'll use in later homeworks in class. So you need to be familiar with these. So here's the Cannonball Srp model. So this model for Srp acceleration just says that Srp causes a force directed away from the sun. And the magnitude of the force depends on how far you are from the sun, which is R, the size of your spacecraft facing the sun, which is A, your area, mass of your spacecraft, of course. This P sub phi is the flux, the momentum coming from the sunlight. CR is your reflectivity parameter, which is, you know, nominally equal to 1 plus rho, where rho is the actual physical reflectivity of your spacecraft. But really, CR is the parameter that you end up fitting, like in an orbit determination process. And we'll talk more about that later. And then U hat, of course, is the direction, you know, to the sun. Okay. So, yeah, I think that's about all I'll say here. So you need to take some partials of this for your homework. Okay. So you can do that. I think the other interesting thing, this down in the bottom here, this is a picture of the Legios spacecraft, okay, which looks a lot like what?
Cannonball.
A cannonball, right, which is where the Srp, the name came from. Right? Sorry, one sec. Do most spacecraft look like this? Right? No. Okay. Huh? Yes, kind of, right? It still has, yeah. Right, very few spacecraft actually look like this. So the Cannonball Srp model is what almost everybody uses. And depending on your mission, that might be just fine, or it might be an awful approximation, right? Because basically how you get to this form of the acceleration is that you're literally modeling your spacecraft as a sphere. So like all the specular reflection and sideways reflections that would go, you know, like this way and stuff, those all cancel out perfectly because you're a sphere, right? It's like a physicist's dream. But in reality, our spacecraft never look like this. They have big flat panels that are tilted in different ways, and you get forces that are not along that U-hat direction. Okay, so if you want something really high precision, like GRACE, again, for example, they don't use the Cannonball model, right? They have a more high fidelity model. Okay, did you?
Notation C and C.
Oh, sorry. So phi is flux. So it's like 1357 watts per meter squared or something like that. I'll include it in any homeworks that we do, what value to use. And then C is speed of light. Okay, and then last slide real quickly. For dynamics, third body perturbations. Okay, so we're in orbit about the Earth. We carry about R, right? We carry about our orbit about Earth. this is how you figure out what the acceleration due to the sun on your spacecraft is. Okay. In this case, I just drew a picture of the sun. Of course, you could use this for the moon, right, or for any, other planetary body, right? Whatever you want. So you also have to do partials of this guy in your homework. Okay. So everything you need is on this page, though, right? It's just vector math. Okay? Any other questions? Cool. So let me know if there are questions on the homework. Please post them to the discussion board, and all of you pay attention to that so you can help each other. And I'll watch that too. Okay? See you next week.